Then you've seen that in this industry too.
So change orders happen all the time. You're gonna get changes in the project today. That'll be at the end of class. I'll talk about that. But we have some timeline changes because we had some snow days, right? So we've got prototype 1 coming in on Thursday. Engineering calculations are not due until the 23rd, so those slid back, and we'll talk about those today. Project prototype 2 is on the 6th, which is only a week before the final delivery on the 13th. So everything has compressed, which is a pretty standard project. In life, it always compresses. But just note those changes. There'll probably be a notebook check on Thursday. There is a recorded guest speaker that is up today on the 18th. That's here and here, week 7, and here on Tuesday. So, oops, sorry, it's on Thursday. I just put it here to remind myself. It's there. It's an old one. It's probably 5 years old, but this is what we do when we can't get humans to actually come to class, which I can't get any humans to come to class. Guest speakers will start showing up as a recorded guest speaker. So you just watch an interview with a past student. Fred's super interesting, so that'll be fun. And there'll be a few more that come up. And I will announce them in class, so you have good notice on that. Questions? Questions on any changes in the schedule? Yeah.
We don't get through the video today, but we have to do it like at home, we'll watch it at home.
Yep.
All right.
Yeah, you won't get through it in class, for sure. We'll be busy all class. And you probably don't want to do on Thursday, that's lab time for project. So yeah, this is like a homework thing.
Okay.
Yeah, but you have until the 23rd, right? That's Sunday. You just
Sunday.
can't forget.
The video, right?
Yeah, the recorded lecture or the recorded interview with the past student. So you can't forget to submit stuff. That's easy to do in this class, and then you get a big old 0. So that's the other thing you should do is check your grades, see where you got the big old 0s. A good rule is everybody submits everything, right? There'll be very few things that we just do a 1 submission. I want all students having to deal with the exchange of files. Teams are exchanging files and trying to get documents done. Organizing that information, getting it uploaded, that's your deliverable. That is a constant life experience in engineering. You're constantly sending files to other folks. You don't want to send an old file, you want to send the current file. So you have to have some way to keep track of that. And this is just my way to make you do it, right? At some point, I'm going to ask for a schedule update. So I have the schedules printed here. I look at them each class just to see where I think you should be as a team. So you could think about updating your schedule too. Because now we have timeline changes, right? Your schedule's no longer good. Prototype 1, change the date. Prototype 2, change the date. Adjust that schedule. That's a constant thing that happens to you. You don't usually have control over the schedule, somebody else does, but they're messing with it all the time.
Other than writing it down real quick, where do we, is that where we look to see where we change or where do we change?
You have your schedule,
But I mean, the changes.
Blackboard. So
Oh,
everything's in Blackboard.
okay,
Blackboard tracks this class,
just want to make that.
Yep. right? That's that calendar that I have up. That's Blackboard.
Yeah, that guy.
And I don't just randomly change it, right? Whenever I change it, I in class say, we've got a schedule change. Yeah.
Appreciate it.
At work, they'll randomly change it. So the first thing you do when you get to work is you get your coffee, you do whatever you got to do to make yourself happy, and then you check schedule. So that could have changed overnight. Night shift could have changed it. Swing shift could have changed it. Whoever changes it. All right, good. Today we're going to do calcs. And I'll give you 3 things that you can do calculations on your project. You can do all 3. That would be next level achievement for a team. But what I'm looking for is a calculation package that has at least a couple of the three that I talk about. I'm gonna talk about bending stress. I'm gonna talk about tensile stress. And then a weight calculation. So we should do the weight calculation for sure. And that's not taking your device and weighing it, right? That's what you would do in the end to check your weight calculation maybe. But the concept is you would be doing this weight calculation prior to the finished design. So you know how much it weighs, right? Maybe there's a weight constraint. All right. Good so far? Oh, the numbers went up. That's great. We only had 8 people at 8 o'clock or 9 o'clock, so I was worried that we lost 16 people. That'd be bad. My dean's gonna be like, "What'd you do to those poor students?" I'm like, "Geez, I just showed up. That's all I did." All right, let's talk about calcs. Here's an old school set of calcs, and this is for me. And when, I don't even know, is it dated? Anyone see a date? Oh yeah, look at that, 1996. Wow, yeah, I've been around a while. This is my garage calcs. I found this guy, Dowler, Gerald L. Dowler in Silverton. That's his stamp. So if you're wondering about a professional engineering stamp, that's what they look like. So anyone know how you become a professional engineer? You get licensed. What's that mean?
You have to go through like a board.
You have to sit for a big old test, right? So I'll spend more time talking about the PE, professional engineering license, in another class, but here's the concept. You got to, in the state of Oregon and in most states, not all states, Oregon just switched to this 5 years ago. You have to have a bachelor's degree in engineering to pursue a professional engineering license. 6 years ago, you could do it with a 2-year degree. That was super rare because it's not an easy test. The first test you take is called the Fundamentals of Engineering exam, the FE. It used to be Engineering Training, EIT. So I took the EIT way back in the day when I was in college. Passed it. You don't know what your score is. You know if you passed or you failed. And it takes an 80% or above to pass it, the FE. And the PE is the same way. You don't know what your score is. You get a piece of paper that says you passed or you failed. That's just rough because you don't know how much you failed, right? And so I passed it. I think I got lucky with the FE. I took it my junior year, and that was because I knew I was going to fail it, so then I could take it my senior year, and I actually passed it. So it's like, wow, that's cool. But you have to pass your FE, and you should do that somewhere near your bachelor's degree finish, because that's when all the knowledge is current as it's going to be, right? My son just got his job. He's taking the FE at the end of this month. That's a good process. If you wait a couple months, everything just, right? Everything from this term is going to be gone next term. Like long-term retention is really tough. For the FEs, there's classes you can take and there's softwares you can buy that prep you that are really, really super valuable. Then you have to work for 4 years. After you pass the FE, Fundamentals of Engineering, you have to work for 4 years and you need to have a mentor that is a PE, professional engineer. Most large companies have that. Most small companies do not. So if a professional engineering license is in your future, you think, then you're going to want to go to work for a company that has PEs. You don't have to work for the PE, but they got to be employed by that company. And then they will mentor you over 4 years. They'll just look over your shoulder and make sure you're getting some good calculation practice. Make sure you're prepping for the PE, the professional engineering license test. Then you can become a PE, right? So it'd be 4-year degree, college 4-year degree, 4 years of mentorship, and then you can sit for the PE. The PE is tough because it's now been 4 years since you went to college. And I like everything's gone. You know what your job is, and you're good at your job, but that's just going to be one little thing of your engineering education. So It's a fair bit of commitment. But if you pass it, then you get one of these. You get a stamp. And then you can stamp things and you can fully take responsibility for whatever you're stamping. It is 100% your responsibility. He stamped this. If anything happens to my garage over the length of its life that shouldn't have, right? Then he's responsible. He could be looked up. You know, if I wanted to sue him or something, or if it, you know, killed 3 kids and the state wants to sue him or whatever. That's the thing. If you become a PE and you start stamping things, you're responsible for it. You're gonna carry a healthy insurance policy. That's what you're gonna do. So if you plan on getting a PE and you plan on getting a stamp, you better plan on using it just to pay for the insurance, because the insurance is very expensive, right? Or you go through a company, right? So the PEs at Boeing, they don't pay for insurance because Boeing is insuring them. So that can be the case too, that the company wants you to get your PE, you get your PE, now you're going to be stamping things for the company and they're going to cover you. Right? So there's ways to do it without, when you're stamping for a company though, then you're not getting that direct profit from taking that responsibility, the company is. So there's pros and cons to, you know, how you want to work that. Most of these folks, they get their PE. I don't have my PE. I had no need for it. I'm not going to go stamping things. I don't want that responsibility. I'd rather hire Gerald for $2,000 to design my garage and give me this calculation package. Okay. He can take that responsibility. I'll pay him. Yeah. You have to get it renewed. Yeah. It's easy renewal though. Once you get it, it's like a nursing renewal. You have to have so many continuing education credits to keep it renewed. They're simple in the end. You do have to get a different one for every state. That's a little more difficult. Yeah.
Are all the stamps the same, or is it like company exclusive ones?
No, they're not all the same, but they're not company exclusive. They're human exclusive. It's for a person, not a company.
It's like Boeing has like their own stamp.
No. Nope. And they're different now. Like this is truly a stamp. I think you still, like, you have to buy your stamp, right? So you buy whatever you want, but you can get the ones that emboss. Those are kind of cool. Like you can press it and actually change, you know, makes it 3-dimensional, but those are spendy. This is just like a stamp thing, you know, and then you sign it.
Does it restrict this, whichever you have your degree in, doesn't it restrict you from?
It does. Yep. If you're a mechanical engineer, then you can only do mechanical engineering type work. You could be foolish enough to stamp anything, but you would never do that. Yeah. So he's a structural.
You said you have to do one for every state. Is that like a 4, like, you know, you gotta have the 4-year?
No. You can transfer your, I don't think it's even another test. It might be more of like a portfolio of your work in that state, and then you turn it into the board of that state, and then they'll issue you a stamp. Kind of thing. Yeah. Good. All right, good. These were hand done, so calculations can come in many forms. You know, at the college, you all are going to do calculations like this. They're going to look like homework problems. This is a class I teach right now. It's statics, right? So it's going to have a graphic. It's going to have a problem statement normally. This doesn't have everything. I have a slide that shows you kind of everything. But it's going to have calculations in it, and then it's going to have solutions. All numbers should have units, right? So there is a basic format to calculations in academia, but there's also kind of a basic format outside. It can come to you a lot of different ways. So a lot of computer generated calculations are out there now. This is a beam analysis. It's an LVL. So if you don't know what an LVL is, it's like a piece of plywood. It's laminated layers of wood, and we can take that grain of the wood and we can cross it. Right? So that's what plywood is. It's really thin pieces of wood, and then we can take the grain and cross it and build a beam that way.
Like a floor joist?
And it's hell for strong.
Like a floor
Excuse
joist?
my language. Well, floor joist can be regular timber. Or it
I
can
know
be
that the new ones are making where it's
a
like.
truss joist. Yeah, that's correct. So this one's rated at 1800. So that's an 1800 bending stress. 1800 PSI. Okay. Standard wood is about 800 PSI in bending stress. So if you just had a tree and you just cut a 2x12, right, and you use that 2x12, bending stress of about 800 or 900. This is a pretty thin LVL. It's only 1.5 inches, right? So it's pretty thin. That's why its rating's down pretty low at 1800. You can get 3800 LVLs, 2800 LVLs, all different kinds.
Still pretty strong.
Oh, it's very strong. This is the load that's put on the beam. So this is the beam and its span. I don't know if you can see that. I can't even see it. It's like 18 feet, 15 feet or something, 15.8. I can't, it's too small. And it's got some load rating on it. And then the software is mostly doing the calculations here for you. So if it's a simple beam, this is a very simple beam. It's just got supports here and here, and a load. And then there's some other constraints that get put in, and it passed under this load condition, right? So the software will give you kind of a calculation package. This is not accepted at the county. The county wants to see the formulas that are run. So you'd have to do kind of a different printout that would show. This is mostly just for sending to clients that you want to use this beam, it passed, you could use it kind of thing. Right? So here's another set of calcs. Looks more like what we would do in school. I think you'll find engineers that have been out there a while are just going to run some calcs on paper. Like that's how I do it. I run them here first, and then I'll run them through a software as a check, because you're no good at checking your own work. I don't know if you've all tried to do that before, but it's really rough to figure out if you've made a mistake or not. Looks good to me, you know. So it's good to at least run it a few different ways. So I'll run it on paper like you will do and we will do today. And then I'll run it through a software to just double check it. But something super important, then I would run it by another engineer and have them go through it. And I'd pay for that if I have to. So for you and doing stuff at school, these are the things that we're looking for. You know, if it's a problem out of a book, it should have a problem number. It should have a date for sure. It should have a graphic. Everything we do is we're calculating something. It should have a graphic of some kind. And then as many notes are necessary, and then the calculations. And if it's a solution thing, like what's the answer, then normally that answer is either like underlined or somehow identified, so whoever's looking at the work can go to it quickly. Kind of like this. Like if this was sent to me, I'd look right there first, because it's going to say passed or failed, one or the other. So that's kind of like the answer to the question here. And then I can go back through and make sure the load rating was what I gave them. Because the problem with computers is, you've heard it, garbage in, garbage out, right? So if you don't know what bending stress even means, then you don't even know what 1800 means. And then, you know, if you're looking at a load range and you're seeing like a 400 pound per foot load range, and you know it's supposed to be 800 pounds per foot load range, then you're getting junk out the end. So you really have to know, you know, you have to know what end shear is. You have to know what total load deflection is. You have to know what the span and depth is, and, you know, positive moment, negative moment, that stuff's important. So I'm not a big fan of these. I just am, I guess, old school a little bit. All right. Let's talk about a couple stresses that are pretty basic. Keep in mind, you'll take a whole term on this. So this is very fast. This is way too fast. But we can do it. You all are capable. You all have calculators, right? All right. Before we do that, before I do the stresses on to give you the one that I think everyone's capable of, and that's the weight calc. So I want you to do a weight calc on your project. So the weight calc, come on. Y'all see that? Do I need to zoom in? I'll zoom in. How do we calculate weight? Like if I want to calculate the weight of this yardstick, I don't want to just weigh it, but I want to calculate the weight of this.
That's my property.
Close. We need to know how much what? Mass is here. What's another way of saying volume? We need to know the volume of this thing. Everyone understand what volume is? What's volume?
Massive.
Not mass. Yeah,
It's the amount of material that is in it three-dimensionally.
three-dimensional, yeah, it's how much actual volume is here, three-dimensional measurement of this thing, right? So if I needed to know the volume of this, how would I get it?
Length, width,
All right, let's do it. It's
multiplied by each.
36 inches long. We're doing this. 36 inches long. It is. It's supposed to be 1 inch, but it's not. It's 1.180 inches in this dimension. 1.180. Good so far?
Is it exactly 36?
We're gonna say it is. Probably not, sir. My caliber doesn't, amount of trust tape, maybe. So we're going with 36. And then its thickness is great thought, 0.165.
All right.
Yeah, so how do we get volume?
Okay.
36 inches. How wide was it? What are my numbers? 1.80 inches. And then what was the thin dimension?
6.5.
Point
165.
0.165,
I misheard you on that one.
right? So it looks something like that. 36 inches times 0.180 inches times 0.165 inches, right? All right, what do we get?
All right. I got 10.69.
Inches to the third. Yeah. So to calculate weight, we need the volume of the thing, right? And then what do we need?
Something that indicates how heavy the wood is per.
What's that called? What's that called? Density. We need the density of the material. All right, well, no clue. No clue what the density is. Pretty light. How many cubic inches do we have? I don't know. Somebody Google balsa wood.
Oh, that's.
I think it might be balsa.
I have the density of mine right here.
No, that's
Density is
not
not so
stronger
good.
than.
Let's do balsa wood though. Somebody look up the density of balsa wood, and we need it in US units, not metric units, or we gotta
Really soft.
Google really likes to give you.
I got it here.
Metric. Yeah, the density is got absolutely everything. Can do. Pretty much, especially wood, wood's good, yeah. Could be green, it could be wet.
Wood.
Dry, it should be killing dry. It's endless. Anybody got a balsa density? We're gonna be looking for something like pounds per cubic inch or pounds per cubic foot.
No, I don't. Think of it that little strong.
Say again, 86?
8 to 16 pounds.
All right, so we'll say the density is We'll say it's 8 pounds per foot cubed. That's what we'll say it is. You'll get the same kind of information when you try to get the density of cardboard. And I'm sorry about that, but good luck. How else could we get the density of this? Is there any experimentation way we could get it?
By smacking someone or something?
Huh?
By smacking someone?
No, not by smacking. That's a good idea.
Perch, I think it's perch.
What about that idea?
Yeah, we ain't it, we can get that.
That'll give me the density of this, won't it? So I can get it by experimentation. Is it actually reading anything?
Yeah. So isn't that too short for it?
0.04. No, it's weighing the whole thing.
Oh, okay.
So that volume weighs 0.04 ounces.
I think it's perch. Also, it's snap really easy.
It's on, oh, it's on kilograms. Let's get it off of there. Yeah, 0.10 pounds. So this volume weighs 0.10 pounds. So we can look up the density if we're pretty sure we can get the density, or we can do it by experimentation if we know the volume of a sample. Right? Because this says, oh, it's 0.10 pounds per 10.69 inches cubed, correct? That would give me pounds per inches cubed. And that is a density, right? Gesundheit. Gesundheit. Anybody got this number?
You just, I'm assuming you multiply that,
Don't multiply it, no.
or you divide it.
It looks like a divide to me.
Oh, okay, yeah, because you're isolated. You're not, you're just figuring out what it is for the.
0.00935, yeah. Well, let's get it per foot cubed. That'd be better. How do we get it per foot cubed?
You have to divide it by 12.
Careful,
Where did you all come?
the unit is cubed.
If I did it right, I think it's 0.009 something. And it's 38, and it depends on how many places you want to go with it. Yeah. Oh, let's say that's an actual core if you're rounding up.
So this is called unit analysis when you do a conversion. And I always write it out. I don't try to like, do I divide? Do I multiply? What the heck do I do? I always write it out, always. Even like 12 inches per foot, like I write it out. If I'm gonna convert inches to feet. Especially for somebody else that might be overlooking this. So here's the density we came up with, and if I want it in feet per feet cubed, then I need feet cubed on the bottom. And I need 12 inches cubed per feet cubed, right? Because there's 12 inches, so that's the conversion. You cube the number, you cube the unit. Both of them get cubed. Okay? Now, these cross when I multiply them. That's called unit analysis, right? I want the inches to go away, inches cubed. Leaving me with pounds per foot cubed. So it's not a division, it looks like it's a multiplication by 12 to the third. Right? Because the unit is to the third. So I can take my 0.00935 and 12 to the third it. Yeah, that's carrying everything. You wouldn't want all that. I'd probably just call it 16.2 pounds per foot cubed. Right?
What did you said? What?
I got 16.2. Makes sense?
So you round according to how good.
Yeah. And how confident you are in the information you're getting. Like, I'm less confident, right? Because it's missing some parts.
Yeah.
So it's not actually the full 3 foot by, and it's got another hole there, and it's got a gouge there. And I actually don't even know if it's 36 inches, right? I think it's probably close, but yeah, so there's some lack of confidence.
It'll be a little off.
All right, so then how would we get weight? Now that we have this for my stick, right? Well, we got weight because we weighed it, but if we're calculating, we need the density and we need the volume. If I had more balsa pieces, if I had more pieces out of this material, then I just need the volume of those pieces multiplied by the density and I get the weight. That's the weight calculation that I want. I want you to come up with the density of the materials you're working with. And then calculate the weight of individual pieces. Right? That's what we would do if we were doing a weight calc on a design. If you're in SolidWorks, you can set material to parts and you're going to get weight information per material. And in the end, you can then calculate the total weight of the system. So, individual parts, calculate the weight. That's a good calculation to have in your calculation package. Make it presentable, beautiful, like engineers would. Good? So far? That's a simple one. Pretty simple. You just need to measure your parts, know what they're made out of, and multiply by a density, right? You get a volume.
Multiply volume by density.
Yep. That's right. If you're measuring in feet, then this is a good one to use, right? If you're measuring in inches, then this is a good one to use. So I wouldn't look up cardboard. I would take a piece of cardboard, calculate its volume, weigh it, and now you have the density of the cardboard you used. Because all cardboard's not created equal. There's a lot of different kinds out there. Yeah. Good. Now, you can get as technically accurate as you want and as time allows. If you're gluing things together, you could estimate the volume of glue and you could come up with the density of the glue and add the glue weight in, right? Like it can go very technical if you want to really get tight with your weight. What I want to see is a calculated weight, and then in the end, we're gonna weigh our devices and see how that calculated weight compares to the device, right? It'll be close. Should not be exact. So if you're fudging the numbers, don't make it exact. That's a little not gonna happen. Okay. Questions on the weight calc? It's good. Okay. Let's talk about some more that you could do. Unless there's a question, comment, anything so far. Yeah.
We're gonna be weighing our builds in this factory.
Yeah, yeah. Yep. Right before you test on the final day, you weigh. And if it's so big that we can't get it on that scale, then you'll hold it, stand on a scale. Not hold it, stand on the scale, and we can do the subtraction. I think most will fit on that. Yeah. We only done one so far. Oh, bending stress and tensile stress. Tensile stress is going to be a hard one to come up with for this project, but it's an easy one for me to show you. Bending stress is more complicated. So bending stress, we should be able to come up with something we can do a bending stress on. So that's the thing. I'm not asking you to do calcs on your entire system. I'm asking you to do a calc on one little piece of the system. A structural piece, a somewhat structural piece. Okay? Like if you had wheels and an axle's an easy one to do a bending stress on, right? If you have like a frame, some kind of, mainframe, that would be an easy way to do a bending stress on. If you have a flat surface that has load on it, then we can simulate bending stress. And that you're just going to simulate it, right? We're going to really simplify it. If you look at your device and you're like, I have no idea what to do for bending stress, come to me. I'll show you something you can do. Okay, so let's talk about bending stress. The simplest form of bending stress is like that beam that I showed you. And so if you have a structural member, you'll see that? Yeah. If you have a structural member, we're just going to simulate it as a beam. Okay. So even though it's not a beam, maybe it's a big flat surface that's carrying the load somehow. It's got the egg in the middle, who knows? We're going to turn it into a very simple bending stress calculation. What is bending stress?
The point that it can flex without breaking.
Yeah, it's not failure. So that would be failure stress. So as engineers, you're going to work in the safe region of material properties, right? So we don't want to get anywhere near failure. Most of the time, failure for us is too much deflection. So if you've ever walked in an older home, like from the 50s, as you go across the floor, you can actually feel the floor flexing. Like it'll move. That would be failure today. In today's floors and homes, we absolutely don't let them deflect hardly at all. Not even when you move the piano in. Okay. So for us, most of the time, deflection is too much deformation, right? So there's bending stress on it right now. I'm putting a very little bit of bending stress. And you can't see any deflection, okay? That's the bending stress that we work with. That's safe. This, no. Nobody wants to drive across the bridge and watch it go like this as you go across it. Nobody wants that, right? Although it could do that, we could design it to do that because materials are flexible, especially wood, very flexible. Mild steel, fantastic bending stress. Really flexes really nicely before it fails. That's why we like mild steel so much, because it gives us an indication it's going to fail way before it fails. Like it looks like this, like, oh shit, that's going to fail, right? Instead of just blowing up like titanium. Titanium, boom. No indication, no deflection, and then explosion, right? Titanium is a different kind of material. All right, so bending stress is this. It's the stress that this material can hold in bending and not deflect too much, right? Or any material. So what it takes is, it takes supports and a span typically. The span is the distance between the supports, right? All right. So I'm just going to create a problem. We're going to only work with single loads right in the middle. So if your load is like kind of distributed, we're just going to pretend it's not, and we're going to concentrate that load. And then there'll be supports at this end and this end. This could be wheels. This could be, the span of the stair. If you're like going down the stairs and it's going to touch two stairs at once, then it's supporting your system. Maybe that's the span. Okay. So we do have to design and kind of figure out some of this loading condition. Statics, which is what this is a static analysis. So it's not it flying down the steps and it's not it crashing into the wall. Those are dynamic analysis. And that's way beyond what we want to even try to pull off. But we can do a static analysis like, oh, it's going down the stairs and we just take a snapshot of it. It's not accelerating and it's not deaccelerating. We can do a static analysis. So a car driving down the road at 60 miles an hour, cruise control, we can do a static analysis of that, even though it's moving. It's just not accelerating or deaccelerating. Okay. So if it's supported here and here, then we do need to have equilibrium in the system. So all the forces going down need to add up to all the forces going up. Anyone know that? Who's responsible for that law? Newton, yeah. So Newton was sitting there under the tree, right? And that apple fell. Well, that's the story, at least. And then it stopped on the ground, and he's like, wow, what stopped the apple, right? The ground stopped the apple. How much force? Well, how much force was the apple pushing down? The ground was pushing up, equilibrium. So he got 3 laws out of just basically one concept. Pretty cool. Because he said, oh, if it's not in equilibrium, then it's not in equilibrium. Like, oh, no kidding. Anyway, all the forces down have to equal all the forces up. So if this is 5 pounds, and it's in the center, symmetry. So be kind to yourself and set up the problem pretty simple, right? How much would have to be here and here? 2.5 on each side. Right? And I didn't even know the distance. Like, is this thing a mile long or is it a foot long? I don't need to know that, right? Equilibrium is the sum of the forces in a direction are equal to 0. So the sum of these forces in the y direction are equal to 0. True? It's in equilibrium. It's not moving. Now, it's got 2.5 here, 2.5 here, and 5 here. And we will say it's 6 inches and 6 inches. It's in the center. If it was different, then that changes our loads on these. These are called reactions. But it changes the load on the supports if this is not in the center, right? As this moves closer to this side, this gets bigger, this gets smaller. There's ways to calculate that, but I'm not going to make you do that. Okay? So this is called the translational effect, the up and down effect, and we've captured it. It's good. It's in equilibrium. But now I need to understand, like, oh, well, if it deflected or changed its shape, what would it look like? Want to do this? If it deflected, if it bent, it would bend like that, would it not? That's bending stress. That's the effect of the load at a distance. And what we need to know is, can our material handle it? Can our material handle the bending stress? So we have to be able to calculate it, the bending stress. The formula is MC over I.
Oh, 5 pounds, is that what that?
So this is S for stress,
Oh, yes.
E for bending,
Thank you.
M for moment or torque, C for the C value, which I'll have to explain, and I for inertia. Those are all the parts and pieces of the bending stress formula. If it was tensile stress, it would be S sub T. And different books in academia, not all engineers agree on what this should be called. I'm using S for stress. Sometimes it's the Greek letters, so that's bending stress, and in a lot of books, that's tensile stress. In a lot of books, I think that's tau. I don't know what that is. Beta, something like that, right? So it can be Greek letters in books. I'm just using S for stress and B for bending. So that's the formula we want to run to try and understand what the bending stress is. This will be a calculated bending stress. We're going to calculate it, right? So then you take your calculated bending stress and you compare it to the material that is being bent. And if this is balsa wood, I would need to look up balsa wood bending stress. Okay. So I'm not gonna look it up right now. S sub B balsa. We'll just say it's 400 PSI. Right? But this is a material property. So if you're using aluminum for your struts or mild steel for your struts or titanium for your struts, you gotta look that up. You gotta like, well, I gotta know my properties. Because this is just gonna be a calculated property. And I have to compare it to the actual property of the material, right? Good so far?
What's the value of C?
It's a good question. We're gonna work our way through this formula. C is actually, I'll do M first. So we'll do M, we'll do C, and then we'll do I. Okay, in 10 minutes. This is good. We might have to do this again on Thursday, just right at the beginning of the lab. Might be helpful. Okay. All right, M is called the moment, but it's also a torque. Moment is very engineering term. Torque, most folks know what a torque is. How would anyone want to explain what a torque is? Yeah.
Pretty much like in mechanics, you have a torque wrench and it'll show you how much force that you
He's
have.
doing this. What's that?
Twisting of the material.
Twist, it's twist,
Twist.
yeah.
But
Torque is twisting.
Like a drive line to the axle or to the rear end.
A lot of things twist, yep. So here's what we get. This end, right, is flat, horizontal. But what's it do when I do this? Now what is it? Is it angle? It's on an angle. So it went from flat up to an angle. That's a rotation. That's a torque. So when you bend this thing, it is trying to rotate the whole thing, right? That's rotation. That's called moment for engineers. It's called torque for the rest of the world. We love to do that. We have special names for our own stuff. That's because we're different. All right, so moment is force times distance. It's a simple calculation. Force times distance. When I do this to the yardstick, where do you think the most stress is? In the center, in that very center spot. Okay. So that's where we need to know the bending stress is at the very center. So if I am here at the very center, and I want to know what's going on here, this is just applied right at the center. So it doesn't create any moment. It would be 5 times 0 because I'm right here. No distance. D is for distance. So where's the furthest away force?
What's that? Sides, did you say?
Yeah, here.
Oh,
The furthest away force from that point. This one's right at the point. Right? It's out here at this 2.5 or this 2.5. That's why we're in the center. So it's simple. Right? So our force is 2.5 pounds. At how far? How far away is it from my point?
6 inches.
Yes. What's my moment? Who's got a calculator in this class? Don't do it in your head. Don't ever do it in your head.
15.
See, you were way off. How much?
15.
15, and what's the unit? Inch. Pounds, not inches per pound, it's an inch pound. This is like,
What's an inch?
this is the core of life, just so you know. This is like the meaning of life.
What's an inch pound?
What's an inch pound?
I know, and is that count per inch?
No, it's an inch pound. It's torque.
A torque, okay,
Yeah,
okay.
because what do we do with the unit? We multiplied it. Yeah, it's an inch pound. It's a pound inch, but I can't say that comfortably. For some reason, inch pound is more comfortable for me. Same thing, pound inch pound, right? That's our M. That's this. Good so far? Not too bad, as long as you get a little drawing and you can do this moment calculation. All right, C, what's C? C is and this is, I'm just gonna have to show you what C is. So this is our beam we're working with, right? This is the cross section. So when someone says cross section, they mean like chop right in half and look at it. It's this rectangle. That's a bad. There, that one's better. Well, I've got a chip out of it too. But you know what I mean, right? Cross section. That makes sense? So C is the distance from the outer edge to the neutral axis of your shape. The neutral axis of your shape is the geometric center. So C is the distance. So you've got to have like a little picture of the cross section. So I'll draw it here. Kind of in line with my beam, right? But that's what the cross section looks like. Agreed? Now that we kind of know what cross section is. And what was this thickness?
The 0.165.
0.165. So here's the neutral axis of this little beam. It's the geometric center. And if you have a rectangle, it's like the simplest one. And here is C, outermost fiber to the geometric center. C. Of course, C changes with the different shape. If it wasn't a rectangle, if it was a pipe, it's from the center of the pipe to the outermost fiber. If it was an I shape, it's from the outermost fiber to the geometric center. So it's very dependent on shape. What would our C be?
You have to.
Yeah, exactly. It's going to be half of the 0.165. C is going to equal 0.165 divided by 2. Mike.
What's define fiber? I mean, it's not like right at the very end. So.
Fiber, outermost fiber is this surface.
Oh,
Outermost fiber is this surface.
okay.
So if this was like an L shape, your C in one direction is different than your C in the other direction, but we don't need to get that complicated.
Why are we measuring it from like the short end?
Because that's the position I loaded it. It's a great question, right? I've always been doing this. I haven't been doing this. Because this way it's really strong. I can't deflect it, right? But this way is the way I loaded it. So that's the position of it. It's perpendicular to the load. Yeah, good question. All right, so now we have C. We just need I.
The calculation is always the same, density, as far as density goes compared to strength, because I know that, like say you got some hours or whatever that are really light.
Yep.
But really strong.
Yep.
So the density is always the same calculation.
For bending stress, always MC over I. Yeah. So you'll notice in here, there's no material properties because that's just a calculated bending stress. This could be made out of silly putty. Doesn't matter. We're still going to calculate the bending stress and compare it to silly putty and then say, silly putty's not going to work, right? It's not even close. I'm guessing balsa wood's not going to work for this load condition, right? But maybe it will. I don't know. So yeah, it's independent of the material. When the material comes into play is when you compare it to something.
Gotcha.
That makes sense?
Yeah.
Okay. The last one is inertia. I know we're out of time, so I'm going to do it quick and then we'll do it again on Thursday. And this is area, moment of inertia. Different than dynamic inertia. You might be thinking inertia is I take this weight and I throw it at you and then you get hit by the weight. That's dynamic inertia. This is area moment of inertia, and it's strictly a mathematical calculation that we need. That's all it is. Mathematical gymnastics. It is an indicator of resistance to bending. It's completely based on the shape of your beam. the shape of your beam. So inertia for this is different than inertia for some other beam. Right? As the cross section changes, inertia changes. So we literally just have to calculate it. There are formulas for inertia for different shapes. If it's a triangle shape, we use that inertia formula. If it's a round circle, if it's a hollow round circle like a pipe, we look up the inertia formula. If it's an L shape, we look up the inertia. If it's an I shape, we look up the inertia, right? Every shape has its own inertia. What is our cross-sectional shape? It's a rectangle, right? Rectangle inertia is base height cubed over 12. I of a rectangle. You can look them up. They're all over the interweb. And they're all over my, base height cubed over 12.
I didn't see it right. That's all right.
Base
Yeah.
height cubed over 12.
That little.
What's our base?
One inch, or was it,
What was our base? 1.80?
1.10?
1 is it 1.8 or 1.8?
1.180.
1.180 inches. What's our height? And what do we do with the height?
Right by 2.
We cube it. We divide it by
Oh.
2 for C. And then we have a constant down below 12.
That formula where you don't divide it by 2 for that.
So that's our rectangle, right? Our rectangle looked like this. And this was our base, our height. What number is being cubed? The height.
Oh, okay.
Yeah. So our height is really thin. How's my resistance to bending? It's not good. It's terrible. Right? I can bend it super easy. What if it was this way? Then that would be being cubed. That's going to drive the inertia number way the heck up. And so that's an indication of bending. I'll literally have a difficult time bending it. Like it's super strong in that direction. Right? So inertia would go way up if we put our beam this way. But we don't. We have our beam this way. And our inertia is going to be pretty small, I'm guessing. Anyone calculate this number?
It's, yeah.
What is it? 4.17.
1.7256.
That's good enough. What are the units of inertia? Crazy. Extra credit Thursday if you can explain what inches to the 4th is. I have no idea. All right. That gives you I, that gives you M, C, and I. Benny Stress can calculate. We'll finish it on Thursday. Good job hanging in there. That was a lot.
Is it because the fourth dimension is time?
So that's what I've always known as the 4th dimension is time. And but time's not in this analysis whatsoever. So when you look up inertia, it literally says a mathematical calculation that engineers use. That's, and they end at that. So it really, what's really nice about inertia is it is an indication of bending resistance in the shape that you've chosen. So if you choose this shape for bending, 4 is a super trash number. It's super low, right? If you did it this way, just switch these two numbers and cube the 1.1, your inertia is going to go up to like 5 or 6 times this inertia. And I mean, if you try and bend this way, This is not going. This way is just like, I could bust it easy. This way, I don't even know that I could bust it. It's gonna twist before it busts.
Yeah.
So that is the nice thing about inertia, is it is an indication of it.
Yeah, nice job. Sorry I went over. Thursday.
There's that.
Unless you got.
I was guessing that.